Okay, hello everyone. So in this video, I'm going to be talking about transformations of radical functions. So before I get into the video, I'm going to just remind us what a radical function is. And basically, a radical function is a function that has a root in it. So whether that is a square root, like the function on the left of your screen right now, or a cube root, like the function on the right of your screen right now, we are going to be looking at those functions and their transformations. And transformations basically means that right now you're looking at the parent function, and that's written on the screen, and you can see that here. The parent function for the square root, it's just the most basic version of the square root function. So y is equal to the square root of x. Whereas the parent function for cube root is y equals the cube root of x. It's the most basic cube root function you could possibly have. Okay, we are going to add to that, though. We might add a number, subtract a number, multiply a number, and that is going to transform or change the function from what the parent is to a slightly different version. Before we continue, something really important to recognize is the endpoint and point of symmetry of these functions. Remember that square roots have endpoints, whereas the cube root function does not. And if you'll notice, the endpoint of this function is at 0, 0. That's really important because that is something that is going to be changing when we transform this function. And the same thing is true of the point of symmetry on the cube root function. We've talked about how the point of symmetry is that point in the very middle of the function. It's sort of where it turns, right? It almost becomes vertical right at that point. And that also is at 0, 0. What I mean by the fact that the endpoint is going to move when we transform a function is maybe instead of having the square root where it is, like right here, maybe we'll move it left and down a little bit. And maybe it'll start here and it'll go like this. Okay, we may even flip this upside down and reflect it over the x-axis and it'll look something like that. Okay, but in different transformations, the endpoint might change, just like the point of symmetry in the cube root function would also change. Okay. So this is here to show us basically the standard form of a square root function. And that is what is written up in the top of the page up here. Okay, that's the standard form of the function. The letters A, B, H, and K represent places where I could write another number that would transform my function. If I put a number where the letter H is, that will horizontally translate my function. That means my function will either move right or left. Okay. This is actually the trickiest of all of the four, so we're going to come back to that in a second. But I'm going to keep moving for now. The next part we have is K. If I wrote a number where K is, so if I add or subtract a number at the very end after the square root symbol has ended, that would shift the function up or down. An example of a function that would be shifted up could be y equals the square root of x and then plus 3, right? If I add 3, it would shift 3 units up. Whereas an example where we would be shifting down could be y is equal to the square root of x minus 4. Since I'm subtracting, it would shift the function 4 units down. And again, we call that shift a translation. And hopefully that terminology is feeling familiar to you from what you learned in geometry last year. The next part is A, and we call that a vertical dilation. Basically, if you put different numbers there, it's going to change how steep or shallow the graph is. So instead of having a parent function that looks exactly like this, if I put, say, the number 4 in front of it, it would just increase a lot faster. Okay, but we're not really going to be looking at other numbers there. We're really just looking at whether or not A is negative or not for now. Like that is what we're going to cover. So we are just looking basically at, is there a negative sign out in front of the square root symbol? Okay, and if there is, then we have a reflection over the x-axis. Okay, so that would be if you had something that looked like this, a negative in front of the square root symbol. And if the function got reflected over the x-axis, instead of looking like this, the graph would look like that, right? It was just reflected right over the x-axis. So that would be like your graph. Okay, I'm sort of making weird things with the eraser, but you get the picture, hopefully. Okay. After that, we're going to talk about horizontal dilations. Sorry, I thought my screen wasn't recording for a second. I got concerned. Okay, next we're talking about horizontal dilations. And that, again, like a vertical dilation would basically affect the steepness of the graph. But once again, we are just looking at whether there's a negative or not. So if this b value has a negative sign, so for instance, if you had something like that, where there's a negative in front of the x, but under the square root symbol, that would be a reflection over the y-axis, which would give me a graph that goes like that, because it's reflected over the y-axis from the original. Okay, so hopefully you gotten all those. I know I kind of accidentally erased my screen. That's my bad. But I'm going to go back to H, because I told you that H was a little more complicated, and you'll notice I didn't actually give examples for when we would shift right or left yet. So as you can see here, it says that if H is positive, then I'm going to shift right. And if H is negative, I'm going to shift left. That's kind of intuitive. We think of right as positive and left as negative. But I want us to look at the form of this equation really carefully. It says x minus h. So let's say I want to plug a value in for h. Let's say I want to put the value 3 in there. That would become the square root of x minus 3. Okay, I plugged in the value positive 3 for h, because the standard form of my equation has that subtraction symbol, that comes out to x minus 3. Okay, so if I had the equation y equals x minus 3, that is actually going to translate my function 3 units right. Okay, and the same thing with left. If I were to plug in a negative h value, it would end up looking like an addition, because the square root of x minus, that's part of the form, and then let's say negative 4, right? Well, that simplifies to the square root of x plus 4. Okay, so I plugged in a negative h value, but it looks like an addition. It looks like this here. So that function I just wrote would actually translate your function 4 units to the left. So that's why these asterisks are here. H works in the opposite way of everything else. So when you're looking at H, you're thinking about the opposite of what you expect based on the symbol, the addition or subtraction symbol that you see. Okay, one way I remember that, and I probably mentioned this to y'all in class, is that a teacher once said to me, it's opposite day inside the parentheses. So you can see how that part is under the parentheses in the standard form. Okay, it's not always going to be written as parentheses, but essentially a square root symbol is a form of parentheses, because parentheses are just sort of like enclosing stuff that can't be pulled out of it, and you can't pull anything out of under the square root symbol. So under that square root symbol, inside the parentheses, it is opposite day. So think the opposite of what you expect. Okay, and then last thing on this page that I'm going to point out is our endpoint, HK. So we get our endpoint from any numbers added or subtracted in an equation. Usually the endpoint of my parent function is 0, 0, and I get that because when I just have y equals root x, no number is added or subtracted. So that gives me the 0, 0, right? H and k are zeros. But if we are adding and subtracting numbers, so let's say x minus 4 and then plus 3, you're going to get the endpoint from those values that are added or subtracted. Remember that under that square root symbol, it's opposite day. So the number there, while it says minus 4, I'm really going to be writing a positive 4. And then outside of the square root symbol, it's just as we would expect. So I write the positive 3. And that would give me the endpoint for this function. Okay. I just like sprayed water all over me, so that's good. Anyways, we're gonna move on. Okay, so I'm gonna go through one example really slowly and then a couple examples a little more quickly. So here I have things color-coded. So I'm gonna write a transformation down here. Oh, I don't have my pen on. I'm gonna write a transformation down here, and it's gonna match with the color of where that is found in the form of my equation. So basically, moving left to right, I'm starting with this negative sign that's in green. It's outside of this square root symbol out in front. Since there is a negative out in front, that tells me that I have a reflection across the x-axis. And I just abbreviated the word reflection to REFL, reflection across the x-axis. Anytime there's a negative sign in front of the square root, that is what you have. Okay. And then after that, we're looking at this negative sign inside the square root symbol. So if you have a negative sign inside the square root in front of the x, so before the x, that's going to be a reflection across the y-axis. Okay, and again, anytime you see that negative in that position, it would be a reflection across the y-axis. And then as I look to the 4 and the 5, I have x minus 4 under the root symbol. I know that under the root is controlling left or right, and it's the opposite of what I expect. So this is going to be a translation, okay, or in other words, a shift or slide, but translation is the technical word. A translation of 4 units to the right. Okay. And then the 5 that's hanging out on the outside of the square root, right? It's just at the end after the square root. That is going to control my vertical shift or my vertical translation. And that is going to be a translation of 5 units up because remember on the outside, it is exactly how we would expect. So I'm adding, so I'm going up. And then my endpoint, again, I'm taking it from that h and k value. So I do the opposite of what I expect here, and I give it a positive 4, and then I take that positive 5, and that also gives me my endpoint. Okay, now we're going to do this again with a slightly simpler function. There's only 2 transformations here. There's a negative outside my square root, and there's a subtraction after the end of my square root. When I find my endpoint here, you notice there's no number added or subtracted inside the square root symbol. So I'm not moving right or left at all. I just have 0 for that x value, and then I'm going to write -3 for that y value. Okay, and then when I list my transformations, I start with that negative sign out in front, and that tells me that I reflect over the x-axis. Okay, and I also have that -3 at the end, and that tells me that I translate 3 units down. Okay, those are my 2 transformations. The 3 units down, that can be seen in this endpoint. So if I put the endpoint on the graph, that would come to like right here, right? 0, -3. And you can see how that has moved 3 units down from the parent function. But because I've also reflected over the x-axis, my function is going to look more like this now. Okay, that's kind of a rough sketch, but that's what it's going to look like because instead of increasing, it'll be decreasing. It's been flipped over that axis. Okay, now we'll move on. Let's skip to this one. So here, I once again have 2 transformations, that negative and that right there. Okay, my endpoint, again, I have that number under the square root. So that's the x and its opposite. There's nothing outside the square root, so that's just 0. When I talk about my transformations inside the square root symbol, that negative sign is going to be a reflection across the y-axis. Again, that's anytime the negative is under the square root. It's a reflection over the y-axis. And then that -2, since it's under the square root, I'm thinking opposite of what I would normally think. So that's actually going to translate right 2 units. And if I go to graph it, I can graph that endpoint of 2, 0. That kind of takes care of that horizontal shift, right? I've already moved it right 2. And since it's a reflection over the y-axis, it goes the opposite direction like that. Okay, we'll do this as our last square root example. So again, I'm looking for the endpoint. The x comes from under the square root symbol. So I have to do the opposite of +6, so -6. I have this 9 on the outside. I write that as is. So my endpoint is -6, 9. And then there's one other part of a transformation. So I have the negative sign on the outside of the square root. And again, if a negative is outside the square root, that tells me that I have a reflection across the x-axis. And then I have 2 more. The +6 under the square root tells me, again, opposite of what you would think. So +6 tells me left by 6 units. And that number on the outside at the end, +9, tells me that I am also translating up by 9 units. Okay. Now we're going to look at the graph. If you are trying, actually, I'm going to skip that one. If you're trying to figure out what graph might match up with a function that is given to you, think about what the transformation is. Think about what the endpoint is. So I'm going to start by finding the endpoint. So the endpoint for this function here would be 1, 0. And I know that again because I take the opposite of -1, and then there's nothing added at the end. So that's the same as adding 0. So this is my endpoint, 1, 0. So right away, I'm looking for where the endpoint is on these graphs. And this is already out because that has an endpoint of 0, 1. So that's like not even in the picture. I'm just completely ignoring that, right? And now I'm just deciding between my other 2 graphs. So let's look at this for a second. There are 2 negative symbols in here. So that tells me that I'm reflecting over the y-axis and over the x-axis. So from my original here, I want to reflect over both axes. So let me start with the x-axis, and I can draw a reflection like that. And then I'm also going to reflect over the y-axis like so. So this third function I just drew is the correct shape, and that matches the shape of this graph here. So I know that this graph matches the function. Okay. So that was square roots, and don't worry, this video isn't going to go on for like hours. But cube roots are also part of radical functions. The good thing is that cube roots are transformed in the exact same way as square roots. The only difference is that the point of symmetry is moving instead of the endpoint. So remember when you think about a square root function, it looks something like this. It starts in the middle of the graph, whereas a cube root function continues forever. Okay, so there is no endpoint, there's just a point of symmetry in the middle. So that is the only difference really, is that I won't ask you for the endpoint, I'll ask you about the point of symmetry. So we're not going to do a ton of examples with this since they're so similar. But again, this is the same chart I showed y'all earlier. Okay, the only difference is now I've put this cube root up here, right? I put the little 3 there to show you that we have the same exact standard form. And note, again, the point of symmetry, it's HK, just like the endpoint was in a square root function. So literally you get everything the same way. You just don't have an endpoint. You have something called a point of symmetry, but it all acts the same way. So when I go to look at this transformation, first I'm going to find the point of symmetry, and I'm going to do that the same way I used to find the endpoint. So I take these numbers here, and again, under the square root, now it's under the cube root, but it's still under the radical, right? That's going to be the opposite. And then outside is normal. So I have a point of symmetry of 4, 7. And then I'm going to talk about my transformations. So I also, on top of those two things, have a negative out in front. So that tells me that I have a reflection over the x-axis. Okay. I am translating 4 units right, and I am translating 7 units up. Okay. When I go to draw a graph of this, I'm going to start in a similar way. I'm going to try to plot my point of symmetry. Okay. And originally I would think like, okay, I'm going to draw the same shape of this graph, but I have to reflect over the x-axis. So essentially, once I find that point of symmetry, I'm going to be drawing it with this shape here. So it's just an upside down version. But I have to make sure that that point of symmetry actually goes through the point that I drew. So I'm going to draw this same shape, but I'm going to draw it up and going through that point of symmetry above. Okay. Cube root functions are a little hard to draw specifically, so if it looks a little messy, I get it, as long as you can identify what the graph should look like and you can plot that point of symmetry. Okay. I want to do one more of these examples, honestly, and then I think that we are good. But yeah, so this one, I'm going to start again, point of symmetry, opposite inside the root symbol, so that becomes a -1, and then I have 4 from outside. There's no negative signs in this whole thing, so I don't have to worry about any of the reflections. I only have 2 transformations, and one is going to be a translation of 1 unit left, again, always opposite under the square root symbol. And then I also have a translation of 4 units up. Okay, and then last but not least, I go ahead and I graph -1, 4. And since there's no reflection, I just follow the exact same shape of the graph that I was given. And there we go. There we have it. Again, a rough sketch of that cubic. And so that's the last of this type of problem we're going to do. I'm going to skip ahead to one problem where we identify a graph, and then this is going to be where the video ends. Okay, but again, I want to start by identifying my point of symmetry. So my point of symmetry is going to be at -2, -1. Again, I take the opposite of that, and then exactly as is. So, okay, already -2, 1, -2, -1, sorry. I'm saying that falls on this one. It does not fall on this graph. So honestly, I already know that this is the correct answer, but let's investigate a little further just to make sure that it's not like neither of them. Well, the other thing that's happening here is a reflection here, a reflection over the y-axis. So let me think about my parent function and what it would look like if I reflected over the y-axis. So I reflected over this y-axis here. Basically, I'm just drawing the same on the other side. Okay, it does have this shape that I just drew in blue, which matches the shape here. Okay, so it does seem that things check out, and this second graph is indeed the correct one. Okay. And I have literally no idea how to get rid of that. Okay. Awesome. So that is basically the video. So hopefully that was helpful and you feel much more comfortable now in terms of both graphing and identifying the transformations of radical functions, or in other words, square root and cube root functions.